Imagine utter emptiness where nothing exists. As humans, we think something must be there for something else to follow. So, how did it all begin? Saying it started from nothing seems puzzling because, well, how does nothing become something? In the vast universe where galaxies sparkle and black holes swallow everything in their path, there's this intriguing idea: nothingness. It's not just a philosophical puzzle, it's a key element in understanding our universe, fascinating scientists and thinkers for generations. Picture a spot out in space that's almost barren. No stars, no planets, just void. It's like a silent corner of the universe where physics plays by different rules. Let's embark on this journey into that intriguing space of cosmic emptiness, exploring the depths of the unknown and tackling the enigma of what nothing really means. The notion of nothingness is a bit of a head-scratcher, but an essential concept in advanced cosmology and science. For those passionate about uncovering the universe's mysteries, grasping what nothingness truly represents is essential to decoding the complex makeup of the cosmos. At first glance, imagining space as a simple vacuum with neither matter nor energy might seem straightforward. Yet, this doesn't capture the complex reality science has unveiled. In today's cosmology, space isn't a complete void. Instead, it's a rich and complicated landscape challenging our basic assumptions. Let's view this through a scientific lens. Contrary to what intuition might suggest, space isn't exactly empty. It buzzes with quantum fluctuations, where particles and antiparticles appear and disappear out of nowhere. This constant activity gives a lively spin to what we perceive as emptiness. Space is tied to the fabric of space-time, as presented in Einstein's general relativity. Even in places where there's nothing visible, massive objects can bend space-time, influencing anything nearby. Staring out into the cosmos, we can detect faint traces of the Big Bang's roar. The cosmic microwave background radiation echoes from the universe's dawn, a soft reminder that space wasn't always as it appears now. Despite our progress, the concept of nothing in the universe still mystifies scientists and philosophers. There are whispers about places where matter density is nearly non-existent, though these remain speculative. One captivating theory hints there might be areas in the universe where the matter is scarce, almost void-like. If these voids do exist, they might hold key clues about the nature of space itself. Does empty space lack all matter and energy? This seemingly simple question opens up a whole new world of scientific and philosophical intrigue. In everyday thinking, space's void is often seen as a perfect vacuum, an untouched canvas with not the slightest particle or energy. It's an idea that aligns with our basic understanding of emptiness. But diving into the deep waters of cosmology, we find that reality is far more complex and interesting than we'd ever thought. In the world of quantum mechanics, where the tiniest particles rule, the concept of nothingness is continually pushed to its limits. Quantum fluctuations remind us that in even the most desolate parts of space, particles can suddenly appear, interact briefly, and vanish again in the blink of an eye. These tiny, fleeting activities defy our typical ideas of emptiness, breathing life into the void and creating a dynamic background. Moreover, Einstein's general relativity shows us that space and time are interwoven in a complex four-dimensional structure known as space-time. Big objects like planets, stars, or even black holes can bend space, affecting the path of other objects nearby. The idea of completely untouched, empty space is just a fantasy. How does the concept of nothing tie into the mystery of dark matter, and what insights does it offer about the universe's complex design? To unravel this mystery, we first have to get a handle on what dark matter actually is. Unlike regular stuff like stars and planets, dark matter stays hidden from us, showing itself only through the gravity it creates. It's the ultimate version of nothing because it can't be directly seen or easily defined. We first noticed dark matter because galaxies didn't behave as expected. The visible matter wasn't enough to explain their movements. Scientists came up with the idea of an unseen, unknown substance, dark matter, filling the gaps in space and holding galaxies together. This strange nothingness of dark matter turns our usual ideas about emptiness on their head. Even though we can't see it, dark matter has a huge impact, shaping the universe's basic structure. It's a great example of how nothing can be important and impactful. In the web of space, dark matter forms huge networks and halos, providing the framework for galaxies and clusters to form. Without it, the universe we see would be totally different. It acts as a gravitational glue that helps create the stars and galaxies that have fascinated us for so long. The Big Bang Theory says the universe started as a singularity, a tiny, infinitely dense and hot point, about 13.8 billion years ago. It's when space and time began emerging from what might be called nothing in our usual sense. But how does this idea of a cosmic explosion relate to the idea of nothing? To get this, we need to understand the singularity itself. At the Big Bang's start, physics as we know it breaks down. It's a spot with boundless density and no volume, challenging our normal ideas about matter and space. This singularity can be seen as a form of nothingness, a starting point without the usual framework and dimensions we're familiar with. Yet, this apparent nothing was full of potential. The universe expanded from this singularity and went through a phase called inflation, rapidly growing in size. In a flash, a cosmic nothing transformed into a bubbling mass of energy, particles, and the forces we know today. In the universe's early moments, it was blisteringly hot and dense, kind of like a primal soup of particles and radiation. In a very short time, it changed in significant ways, including the creation of atomic nuclei. This cosmic shift led to the stars, galaxies, and complex structures we observe now. Here, nothing becomes a tableau on which the universe chronicles its existence, starting from this explosive inception. Is space's vacuum truly empty, or does it have particles or fields? This question is key in advanced cosmology. We might think of space as a big empty void with no matter or energy. But diving into quantum mechanics, we get a surprising revelation. Space's vacuum isn't as empty as we think. Quantum mechanics, which explains how the smallest particles behave, shows that space is buzzing with activity, even when it seems empty. So, the vacuum isn't as silent as it seems. Scientists talk about something called quantum fluctuations, which are like tiny ripples in a calm pond, but they happen way down at the subatomic level. In these fluctuations, particles and their opposites pop in and out of existence in a blink and you'll miss it dance. They briefly appear out of nowhere, bump into each other, and disappear again in a short-lived cosmic show. These fleeting moments shake up how we usually think of empty space, showing that the vacuum is a lively, ever-changing scene. The vacuum of space isn't just lying there doing nothing. It's actually a big player in how the universe works. It's where fields exist, like the electromagnetic field, controlling the basic forces that keep everything together. These fields are everywhere, even in what seems like the emptiest parts of space. As we dive deeper into cosmology, we start to see that space isn't really empty at all. It's overflowing with these quantum fluctuations and fields, making the lines between nothing and something blur. This isn't just some wild theory either. Scientists use this idea in real-life applications, thanks to something called the Casimir effect. When two metal plates are placed very close together in a vacuum, they attract each other a tiny but measurable amount because of certain suppressed fluctuations between them. This shows just how real and significant empty space can be. Have you ever thought about what role dark matter plays in our idea of nothingness in the universe? Dark matter is this mysterious stuff that makes up a big chunk of the universe's mass, crafting an elaborate story about emptiness and its deep impact. Unlike the stars, planets, and galaxies we can see, dark matter is invisible. It doesn't interact with light, making it undetectable through normal means. Yet we know it's there because it has a strong gravitational effect on everything around it. Dark matter serves as the hidden framework holding everything together across the universe's vast tapestry. It lurks in the voids between galaxies, forming unseen bridges that connect them, acting like the cosmic glue that binds the universe's visible pieces. Without dark matter, the galaxies wouldn't be able to keep their cozy clusters. They owe their interconnected dance to this enigmatic force. Further analysis on a cosmic scale shows something even more mind-boggling. Revealed through simulations and observations are sprawling cosmic filaments where dark matter piles up. These act as tracks guiding regular matter, steering galaxy formation, and shaping cosmic arrangements in a grand design. In what appears to be barren space, dark matter is quietly working as the architect of the universe. The involvement of dark matter pushes the concept of nothingness beyond being just empty voids. It highlights that even in what seems like endless empty space, there's a hidden force actively determining how the cosmos forms and evolves. Dark matter urges us to rethink that interplay of emptiness and unseen forces, reminding us that these vast regions are far from being devoid of meaning or activity. Can space ever truly be empty? Not quite. The faint, ever-present cosmic background radiation challenges the whole idea of absolute nothingness, keeping the mystery alive. Cosmic background radiation, also known as the cosmic microwave background or CMB, is like a timeless signature left by the universe's infancy. It's what remains from the Big Bang's glow, a cosmic whisper echoing throughout the universe, reminding us of the explosive event that started it all. To grasp the link between emptiness and cosmic background radiation, we must travel back around 13.8 billion years. That's when the universe was a densely compact sea of energy and matter, extremely hot and tightly packed. Light particles, or photons, were constantly being produced and absorbed, creating a brilliant, swirling fog that blanketed the universe's contents. As the universe grew and cooled down about 380,000 years post-Big Bang, an extraordinary shift took place. The cosmos went from an energetic, congested state to a more relaxed one. Photons, no longer bound tightly to matter, could now roam freely through space without incessant interactions. This critical turning point is termed recombination. Unfettered by matter, photons embarked on their endless voyage across the expanding universe. Today, we detect them as the cosmic microwave background, a subtle glow of microwave energy soaking every part of the cosmos. It's as if the universe carries a quiet reminder of its fiery beginning. This background radiation, chilling at around 2.7 Kelvin or minus 454.81 degrees Celsius, minus 270.39 degrees Celsius, underscores that space can never be truly bare. Even in the universe's most abandoned reaches, the Big Bang's echo lingers. The 1965 discovery of the cosmic microwave background by Arno Penzias and Robert Wilson was a watershed in understanding our universe's past. It substantiated the Big Bang theory and revealed a vast cosmic structure beyond what we can visibly detect. Thus, when questioning whether space can ever be devoid of everything, cosmic background radiation distinctly reminds us that remnants of its lively history exist even in seemingly empty space. Do quantum fluctuations defy the idea of true emptiness? At the quantum level, where particles and forces play out a dance of probabilities, nothingness evolves into an animated and dynamic space. Quantum mechanics, a physics branch handling particle behavior on the tiniest scales, shows us that even void of matter or energy, space isn't truly bare. Quantum fluctuations, akin to gentle pond ripples, signify this cosmic activity. Within space's apparent emptiness, particles and their antimatter pairs emerge temporarily, forming and then disappearing in a pair dance. Under Heisenberg's uncertainty principle, these fleeting events cause particles to briefly elude the concept of nothingness, emerging from nowhere before vanishing back into it. These quantum fluctuations challenge the concept of perfect emptiness, imbuing the vacuum with notable energy and liveliness. It feels as if the vacuum has its own hidden life force, with particles popping into existence from nothingness and then disappearing again, leaving a slight mark on space's makeup. Quantum fluctuations aren't just theoretical musings, they have real-world impacts, influencing particle and field behavior at the quantum level. They lead to phenomena like vacuum energy, energy intrinsic to the vacuum itself. This energy is thought to contribute to the universe's accelerating growth based on cosmic observations. Moreover, quantum fluctuations have practical effects on particle behavior, influencing how quantum field theories predict and describe subatomic particle actions. In lab experiments, fluctuations cause cool things like the Casimir effect, where two parallel plates close together feel a tiny pull due to suppressed vacuum fluctuations between them. Are there parts of space where matter density is so low it's almost non-existent? To figure this out, we first need to appreciate the awesome variety of cosmic landscapes. The universe is a mix of matter and energy, making up a complex web of galaxies, stars, and celestial wonders. But amid all this cosmic splendor, there are places where matter density drops to levels we can barely imagine. One example is huge cosmic voids, vast, seemingly empty areas within the cosmic fabric. In these voids, galaxies are few and far between, and matter density is way lower than in buzzing galactic zones. These giant voids stretch for millions of light years, and at a glance, they might look like cosmic deserts nearing a state of nothingness. But there's more to it. Even in these broad voids where galaxies are sparse, there's a faint hint of matter, with lone galaxies, cosmic dust, and the ghostly presence of dark matter. Dark matter, a mysterious component making up a large part of the universe's mass, still wields gravitational power, even in the emptiest spaces, knitting an unseen thread through these voids. In the grand scheme, the universe is expanding, and this expansion changes what we think about nothing. As galaxies drift apart due to the universe's growth, areas that once brimmed with matter thin out over time. As a result, the density in these spots dwindles, almost reaching what might seem like nothingness compared to the denser cosmos zones. Yet, even in the emptiest stretches, there's still a quiet presence. Photons of light traveling through the universe, cosmic microwave background radiation, and faint echoes of ancient particles. Though they're so faint, these traces linger, reminding us that the concept of nothing is tough to nail down with certainty, even in the universe's most distant corners. Is there a link between nothing and the universe expanding? The idea of nothing ties into one of the universe's biggest phenomena, its expansion. This link tells a fascinating story that captures our imagination, showing how emptiness and the universe's evolution are intricately connected. Our journey starts with a crucial realization. The universe isn't fixed, it's dynamic. Galaxies, like celestial islands, aren't stuck in place. Instead, they're always moving, slowly drifting apart. This cosmic dance, the universe's expansion, is a critical piece connecting the idea of nothing to the vast cosmic stretch. The story unveils when we look into the distant past. Around 13.8 billion years ago, the universe went through a monumental event, the Big Bang. It was the explosive start of our universe from a singular point with infinite density and heat. At that moment, the universe lacked the structures and matter we see now. It was, in some sense, a state of cosmic nothingness. When the universe sprang into existence, it was incredibly hot and dense, a swirling mass of energy and radiation. In the early moments, particles and forces mingled in ways beyond our earthly understanding. But as the universe expanded, it began cooling down, entering a phase called recombination, about 380,000 years post-Big Bang. During recombination, a major shift happened. The universe's temperature dropped enough for electrons to join with protons, creating the first hydrogen atoms. It marked the change from a charged particle soup to a neutral, see-through gas. For the first time, light could travel through space without constant scattering. This turning point is essential for grasping how nothingness ties into the universe's expansion. It let light move freely everywhere, carrying the first photons, which form the cosmic microwave background radiation. Nowadays, these photons fill every part of the universe, marking the Big Bang with their presence. The cosmic microwave background radiation is basically a glimpse of the early universe, a time capsule from when the cosmos was an energetic and material frenzy. The fact that it exists and is observable underlines the deep link between the concept of nothing at the universe's start and its continued expansion. So, how does this nothingness play a role in forming stars and galaxies? To get this, We need to look back to the universe right after the Big Bang, a monstrous event about 13.8 billion years ago that birthed everything. Back then, the cosmos was an extremely hot, quick-spreading mix of energy and basic particles, stuffed with density and heat. But as it grew and cooled, gravity took over, leading to the creation of structures. Those structures rose from slight fluctuations in the matter density of this early cosmic mix. Although tiny, these fluctuations were crucial for what would happen next. Over time, gravity gently gathered matter in those thicker regions, eventually forming the blueprint for galaxies. It's as if galaxies' beginnings were woven into the very fabric of space, hidden within what seemed like nothing. In those early formations, gas and dust gathered, coming together into massive clouds of matter. Gravity's relentless pull made these clouds shrink further, leading to star formation. Inside these stars, nuclear fusion kicked off, lighting up the universe with starlight. Galaxies holding billions of stars formed like cosmic cities in the vast emptiness. These galaxies, from spiral beauties to mysterious ellipticals, became centers of cosmic activity, their gravitational pulls shaping the universe's fate. So, this idea of nothingness isn't about emptiness, but more like a stage where galaxies and stars perform their cosmic dance. Without this seeming emptiness, galaxies and stars wouldn't have a place to exist. The relationship between nothingness and the creation of stars and galaxies shows the complexity of the cosmos, where emptiness acts as a vital canvas for the universe's story. Does having no matter in space lead to black holes? Black holes, often seen as cosmic pits from which nothing escapes, form from the mix of intense gravity and the absence of matter. These puzzling objects have intrigued scientists, acting as gateways to deep cosmology. Understanding how nothingness ties into black holes starts with massive stars. These stars, lighting up the night sky, also have lifespans. When a massive star runs out of nuclear fuel, it goes through an explosive end called a supernova. The star's core collapses under gravity, forming an incredibly dense region. If this core is massive enough, it can't fight back against gravity's pull, leading to a rapid collapse into a tiny, infinitely dense point. This process, known as gravitational collapse, uses nothingness as a pressure cooker for black holes. As the core collapses, it creates a gravity field so strong that even light can't break free. The event horizon is that critical point where there's no turning back, marking the line between the universe we can see and the unknown world of a black hole. Black holes vary in size. Some, like stellar mass black holes, arise from the remains of massive stars, while others, like supermassive black holes, sit in the heart of galaxies and pack millions or even billions of solar masses. The creation of these cosmic giants is rooted in the lack of matter. In vast empty stretches of space, like the gaps between galaxies, black holes don't form as often, but it's not out of the question. Even in these barren regions, when stars collide or interact, massive stars can form, paving the way for new black holes. Plus, the wide expanse of the universe presents ample chances for building hefty supermassive black holes over time as they gather matter, slowly amassing their gigantic mass. The philosophical debates about nothingness in space echo long-standing questions about existence, the universe's beginnings, and the essence of reality. Central to these debates is whether true nothing can exist, or if it's just a mental construct to help us understand what's missing. One view argues that what we call nothing is actually full of quantum fluctuations, tiny waves in space-time, and leftover cosmic events. Even the emptiest cosmic spaces are buzzing with quantum activity, challenging the idea of a true void. On the other hand, another way of thinking suggests nothingness is the very absence of existence, something beyond what we can comprehend. This raises scientific and philosophical questions about defining or measuring such nothingness. These discussions often turn to what nothing means for the universe's story. Is the emptiness of space a blank slate for the universe's grand tapestry? Or is it a vast void that pushes the limits of what we can understand? The concept of space's nothingness also ties into age-old questions about extraterrestrial life and whether seemingly empty cosmic areas might host life beyond Earth, sparking deep thoughts about life itself. Over time, our grasp of cosmic nothing has evolved with scientific advancements. Once tangled with philosophical and religious ideas, the sky was thought to be permanent and ordered, leaving little room for cosmic emptiness. But as science progressed, our view shifted from the abstract to the observable. Pioneering astronomers like Galileo used telescopes to uncover a universe alive with celestial bodies, debunking ancient ideas of a lifeless cosmos. The 20th century brought transformational changes to our understanding of cosmic nothingness. Einstein's theory of relativity and quantum mechanics, developed by Max Planck and others, offered groundbreaking insights. Einstein showed that space-time is dynamic, while quantum mechanics revealed the pervasive quantum fluctuations even in seemingly empty cosmic regions. A major breakthrough came in 1965 when Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation. This faint remnant of the Big Bang provided strong support for the Big Bang theory and transformed our view of the early universe. In 1980, Alan Guth, a physicist, gave us a whole new perspective on the universe with his inflationary theory. This idea suggests that right after the Big Bang, the universe expanded immensely and quickly, helping to explain why the universe looks the way it does on a large scale. Then there's the study of dark matter and dark energy, mysterious elements that make up most of the universe's mass and energy. Looking into these invisible forces has broadened our understanding of cosmic voids. They play a major role in shaping the universe, presenting a challenge to how we perceive emptiness. These days, our knowledge of what nothing means in space involves understanding the complex interplay between visible and unseen phenomena, familiar and unknown. Advanced cosmology has shown us that even in the farthest reaches of space, traces of cosmic activity linger, whether it's quantum fluctuations or the faint echoes of the Big Bang. What does nothing feel or look like? It might seem odd to try and describe something that's defined by its absence, but exploring this contradiction opens new paths for thinking. The universe often brings to mind images of vast, dark spaces where the lack of matter and energy creates the illusion of emptiness. These giant cosmic voids, spanning millions of light years, might seem desolate and quiet, suggesting that the universe is missing in action. But looks can be deceiving. Even in these barren parts of space, activities are happening on a subtle level. Quantum fluctuations, or tiny ripples in space-time, create brief particle-antiparticle pairs that pop in and out of existence, leaving a fleeting mark. Even though we can't see or feel these fluctuations, they show the universe's hidden activity on the tiniest scales, pushing us to rethink what we consider empty. Thinking philosophically on what nothing looks or feels like leads to deep reflection. Some argue it's impossible to perceive nothing, since perceiving means there's something to notice. In the realms of science and advanced cosmology, understanding nothing calls for balancing observation with abstract thought. This journey nudges us to explore the boundaries of human thought and sensory limits. So, how do human perception and thinking shape our idea of nothingness in the universe? Our senses, molded by evolution to navigate the physical world, are our main tools for experiencing the universe. We experience space through our senses, but when it comes to imagining cosmic nothingness, our senses hit their limits. Picture those massive cosmic voids apparently empty. They seem like a dark void with occasional starlight to our eyes. However, this apparent nothingness hides all the tiny quantum bursts and invisible activities happening in those empty spaces. Our senses, adapted to life on Earth, struggle to grasp these subtle quantum happenings that fill the universe. Quantum fluctuations, little waves in the fabric of space-time, are beyond our sensory detection. They're tiny but significant pieces of the cosmic fabric, testing our understanding of nothingness. Our thinking, involving abstract and philosophical reasoning, complicates our attempt to make sense of nothing. While thinking about what nothing really means in the universe, we're thrown into a mix of philosophical ideas, math, and high-level thinking, navigating an intellectual landscape that goes beyond the physical senses. Philosophical musings on the nature of nothingness challenge us to stretch our minds. Does nothingness really exist, or is it just a figment of our imagination? How do we account for the non-existence of matter and energy when quantum fluctuations and cosmic forces are ever present? Mathematics, our trusty tool for making sense of the universe, gives us its take on nothingness too. In math, zero signifies a lack of quantity, essentially a stand-in for nothing. But even this concept puzzles us when it meets infinity, a notion that goes beyond what our human minds can easily grasp. Technology is our ally in pushing past human limits. It extends our reach with groundbreaking telescopes and observatories. These engineering wonders act like cosmic time machines, letting us look back into the universe's history to see far-off galaxies, stars, and events. They catch light that's been traveling across the universe for billions of years, giving us a peek into the past. The Hubble Space Telescope, for example, is a stunning piece of tech circling above our atmosphere. It snaps breathtaking photos of galaxies, nebulae, and other celestial wonders, giving us a window into the universe's splendor. Hubble's sophisticated tools have uncovered secrets about distant galaxies, explaining how they form, evolve, and even revealing massive black holes hiding at their cores. Ground-based observatories are no slouches either, with state-of-the-art tech that allows astronomers to spot and study cosmic events our eyes can't detect. For instance, radio telescopes pick up radio waves from space, unlocking secrets about the universe, like the cosmic microwave background from the Big Bang. Technology doesn't stop there. It takes us to the stars with robotic missions and space probes. These tools brave the harsh, radiation-packed realms of space where humans can't go. They collect information, take pictures, and run experiments, widening our understanding of celestial objects and their worlds. The Mars rovers, for instance, have roamed the red planet, scrutinizing rocks, dirt, and Mars' whole geology, acting as our eyes and hands on a different world, sparking wonder in countless people. Supercomputing technology is another game changer, enabling us to model and simulate complex cosmic phenomena. These supercomputers tackle heaps of data to recreate the behavior of galaxies, stars, and even model the early universe. Simulations offer scientists a glimpse into the complex dance of cosmic structures, expanding our horizons. Now, consider the James Webb Telescope, which recently launched and underscores just how smart and determined we are when it comes to exploring space. This cutting-edge telescope, known as the JWST or Webb, is set to revolutionize our cosmic knowledge. Launched on December 25, 2021, aboard an Ariane 5 rocket, Webb set off to its home at the second Lagrange point, L2, which is around 1.5 million kilometers, or about 930,000 miles, from Earth. This spot was chosen carefully because it offers a stable place where Earth's atmosphere and the sun's glare can't interfere, which is crucial for the telescope's infrared observations, a light our eyes can't see. The James Webb Space Telescope's mission is to transform our understanding of the universe by diving into unprecedented detail. Unlike Hubble, which mainly focuses on visible and ultraviolet light, Webb is designed to peer into the infrared spectrum. This lets it uncover cosmic secrets cloaked in darkness and mystery. The James Webb Space Telescope, JWST, is loaded with cool high-tech gadgets that let it see right through cosmic dust, revealing where stars and planets are formed. With its amazing infrared eyes, it can spot the dim glow of faraway galaxies, giving astronomers a look into the universe's early days after the Big Bang. By studying the light from these galaxies, it helps us understand how galaxies came to be and changed over time. The JWST is also set to reveal the mysteries of planets beyond our own solar system. It'll check out exoplanets and their atmospheres, giving us essential clues in the hunt for places that might support life and aid in searching for life beyond Earth. It can tell us what these planets are made of and what conditions there might be like, setting the stage for amazing discoveries in the quest for livable places beyond our home planet. Plus, it's got the tools to tackle the universe's dark mysteries, like dark matter and dark energy. Those big mysteries make up most of the cosmos, but stay out of sight. Solving these puzzles could change what we know about the fundamental forces of the universe. In a nutshell, the James Webb Space Telescope is an incredible piece of technology and a symbol of human persistence. It's a beacon of hope for explorers who dream of delving into the cosmic unknown, aiming to tackle our current questions and inspire new ones, pushing us further into the mysteries of the universe. As we advance in technology and new telescopes similar to the JWST launch, our quest to discover life elsewhere in the universe remains ongoing. Imagine if we do find life. What revelations could we gain from that discovery? Lately, there's been a lot of excitement and hope around finding exoplanets, planets orbiting other stars outside our solar system. Thanks to hard work with telescopes like NASA's Kepler Space Telescope and TESS, the Transiting Exoplanet Survey satellite, thousands have been spotted. This enormous number prompts a big question. Could some of these far-off planets have conditions right for life? Scientists have pinpointed certain exoplanets that lie in the habitable zone of their stars, also known as the Goldilocks zone. These planets are at a distance where temperatures could allow liquid water to exist, a major life requirement on Earth. To figure out if exoplanets could support life, astronomers use all sorts of methods, like studying atmospheres, surface conditions, and signs of life-related chemical compounds. For instance, using its state-of-the-art tools, the JWST is set to transform how we check out exoplanet atmospheres and look for signs like oxygen and methane that might mean life is there. Interestingly, discovering exoplanets has shown us a wild variety of planetary setups, from hot gas giants to rocky Earth-like places. Some might be very different from Earth and yet make us rethink where life could flourish. One huge find in this quest for alien life is finding exoplanets in binary star systems, where two stars dance around each other. These spots were once thought impossible for life, but new finds show more places where life might thrive. Astrobiology, a field blending astronomy, biology, and chemistry, examines life's limits on Earth, including extremophiles, organisms that survive in extreme conditions. These extremophiles help us imagine how life might cope and continue on planets with tough conditions. Now, let's dive into one of the many exoplanets humans have found, Proxima b. Proxima b is a fascinating exoplanet located in the habitable zone of Proxima Centauri, spurring our imagination about discovering worlds beyond our solar system. This mysterious planet represents our relentless thirst for understanding the universe. Since its discovery in 2016, Proxima b has grabbed the spotlight in the astronomy world. It's orbiting Proxima Centauri, the closest star to our Sun, and sits just about 4.24 light-years away from Earth. To put that in perspective, 1 light-year equals around 5.88 trillion miles, so Proxima b is like a neighbor in cosmic terms. With its spot in the habitable zone, or what we like to call the Goldilocks zone, Proxima b hints at conditions ripe for life as we know it. This prime location means it might get the perfect amount of star energy to keep liquid water on its surface, essential for life. However, observing Proxima b up close isn't easy. The star it clings to, Proxima Centauri, is a red dwarf, which is way dimmer and cooler than our Sun. This makes it tricky for us to get a good look at Proxima b's features due to the faint light. Scientists use smart methods to learn more about it. They track tiny star wobbles caused by Proxima b's gravity. By analyzing these movements, they can figure out the planet's mass and orbit. Another method involves observing starlight that filters through Proxima b's atmosphere when it passes in front of its star, offering clues about the planet's atmosphere and potential signs of life. The upcoming James Webb Space Telescope, JWST, will play a huge role in this investigation, as it promises to give us a closer look at Proxima b than ever before. This telescope's advanced infrared tools will help examine the exoplanet's atmosphere, searching for signs of habitability. We've touched on exoplanets and their potential to shift our understanding of life beyond Earth. But there's a more abstract question to tackle. What is nothing? Is it within our capacity as humans to grasp that concept? To get closer to an answer, we might need to understand how everything could end. how our universe itself might conclude. One popular theory about the universe's ultimate fate is the Big Freeze, or heat death. This theory is based on the universe's expansion, a phenomenon first identified by Edwin Hubble in the early 20th century. The Big Freeze suggests that the universe will keep expanding, driving galaxies further apart. As it grows, the gaps between galaxies will widen, making the universe colder and sapping its energy. Eventually, stars will burn out and die, casting the universe into a cold, dark state nearing absolute zero. In this scenario, matter and energy will become so scattered that forming complex structures like stars or galaxies will become impossible. Ultimately, even atoms will break apart, leaving the universe filled with particles like electrons and positrons drifting aimlessly. On the flip side, there's the Big Crunch theory. This idea proposes that one day the universe's expansion could reverse, pulling everything back into a single point, similar to the Big Bang's initial state. This cycle implies that the universe could go through endless alternations of expansion and contraction. The current evidence from studying cosmic acceleration and dark energy makes the Big Crunch scenario seem unlikely. Instead, the universe's expansion is speeding up, hinting at a different ending for our universe. Another theory, the Big Rip, suggests the universe could expand so quickly that it tears galaxies, stars, planets, and even atoms apart. As the expansion keeps going, space itself comes undone. Though speculative, this idea sparks intriguing questions about the universe's ultimate fate. Exploring cosmic outcomes like the Big Freeze, Big Crunch, or Big Rip gives us insights into what nothing means in cosmology. Each of these scenarios, despite their differences, address how the universe's structure, matter, and energy might change over time. Understanding nothing also involves entropy, which measures disorder in a system. The Big Freeze ties into maximum entropy, where the universe hits a point of ultimate chaos with almost no usable energy left. Here, nothing can mean the lack of organized structures like galaxies, stars, and particles. On the flip side, the Big Crunch or Big Rip ideas hint at dramatic transformations, challenging traditional ideas of nothingness, pushing us to think beyond our current knowledge, especially with possibilities like extra dimensions or multiverse theories. These cosmic scenarios highlight dark energy's critical role in shaping the universe's future. As an unknown force causing the universe's accelerated expansion, dark energy expands our understanding. Scientists study dark energy to understand better the fundamental forces in the cosmos, while these scenarios help us grasp the universe's basic principles, space-time behavior, and the nature of matter and energy. This deeper understanding aids in defining and conceptualizing nothing in the universe. When we think of nothing, we might picture emptiness or non-existence. But what about time? Is time always in motion, or is it something we created to make sense of reality? One view sees time as a core feature of the universe, matching our daily experiences, where time moves steadily from past to future. Time is intricately linked to our lives, like a clock ticking or seasons changing, guiding events and processes. In modern physics, time is a key part of space-time, a four-dimensional setup, merging space's three dimensions with time. Albert Einstein's theory of relativity well tested and proven, treats time as dynamic and flexible. According to relativity, space-time's fabric isn't static, but can be shaped by mass, gravity, and speed. This view supports time as a fundamental part of the universe, woven into space-time structure. Meanwhile, there's a philosophical angle that questions time's absolute nature. It proposes that our view of time as linear and one-way is a mental construct, a useful way to organize experiences. This angle suggests we impose a time framework to sequence events and establish cause and effect. One argument for this view highlights time's relativity. Einstein's theory of relativity, especially the idea of time dilation, shows us that time passing isn't the same for everyone. It changes based on how you're moving or the gravitational field you're in. Basically, time isn't a fixed thing but relies on who's observing it. This suggests that time might be more of a concept based on perspective rather than a fundamental universe feature. There's even a philosophical angle that argues time emerges from the interactions in deeper physical processes. From this angle, time results from the laws of physics, like how particles, fields, and energy behave. Here, time is more like a human-made concept, something we use to make sense of cause and effect in the universe. Do certain parts of the universe see time acting differently? And if yes, what does that reveal about time itself? One big part of Einstein's relativity theory is time dilation, where time ticks at different speeds for people moving differently or in unique gravitational fields. We've proven this with experiments, and it's crucial for tech like GPS. Satellites up in orbit have to deal with slightly changed gravitational pulls, which means they need to adjust for relativity to beam down accurate locations to us. In places with really strong gravity, like near massive cosmic objects such as black holes, time dilation becomes super noticeable. If you were close to a black hole's event horizon, the point you can't escape once reached, time would seem to slow way down compared to someone far away from it. This is called gravitational time dilation, happening because big objects twist space-time, a concept from Einstein's general relativity. Time also acts funny when considering the universe's expansion. As the universe spreads out, galaxies drift apart, and their light stretches out in what's called a redshift. This tweak not only changes how we see color, but also how time passes. Folks in different galaxies might feel time flowing differently due to this cosmic expansion. Plus, the strange world of quantum mechanics makes the sense of time trickier. Quantum stuff, like particles being entangled or in superposition, implies particles could be in several places at once, playing with our regular idea of time rolling out in a straight line. Could time travel ever be a real thing, and what kooky scenarios or roadblocks come with it? In the land of theoretical physics, several ideas hint time travel could possibly happen, though making it work is a monster of a challenge. There's all sorts of theories sparking talks about time travel, including wormholes. The idea is these wormhole tunnels through space-time might let someone jump through time or space quickly. Physics says wormholes could be real, but creating and keeping one stable needs weird, currently unknown matter with negative energy. There are also closed time-like curves, CTCs. Some equations in Einstein's general relativity hint at CTCs, meaning paths in space-time that loop in on themselves, potentially allowing time loops. To get into and survive these loops would need exotic matter with negative energy, and it brings about weird paradoxes. Then there's the butterfly effect, the theory about small changes in the past impacting the future in huge, unexpected ways. A simple act, like a time traveler squashing a butterfly back then, could unpredictably twist history. There's the bootstrap paradox too, where something sent to the past becomes the very thing that got sent in the first place, creating a loop. Imagine a time traveler handing Shakespeare a collection of his own plays, and then Shakespeare publishes them, creating a mind-bending paradox. So, where did those original works actually originate? When it comes to time travel, it could potentially mess with core principles like energy conservation and causality. Tweaks made in the past might throw the sequence of events into chaos, sparking logical headaches. Igor Novikov, a physicist, put forward something called the Novikov self-consistency principle. This idea suggests that the rules of physics would somehow stop actions in the past that could lead to paradoxes. Essentially, if time travel were doable, the universe would make sure to sidestep any paradoxes. Although these paradoxes and hurdles make time travel a real challenge, they also serve as captivating thought experiments. Shifting over to the multiverse theory, could it give us deeper insight into the nature of time and space? This theory suggests that the universe we know, full of stars, galaxies, and cosmic wonders, isn't the only one out there. Instead, there's a multiverse, an enormous collection of different universes, each with its own unique set of physical rules and traits. One well-known version of this theory is the many worlds interpretation of quantum mechanics. It hints that every quantum event with various possible outcomes leads to a split, generating a bunch of parallel universes, each reflecting one of those potential outcomes. In this viewpoint, our universe constantly splinters into a staggering number of branches, covering every imaginable result of quantum happenings. Another angle of the multiverse theory comes from cosmological models, like inflationary cosmology. According to these models, the young universe went through a period of rapid expansion, and different areas expanded at different rates. In some spots, this expansion stopped, allowing galaxies and stars to form, while in others, it kept going indefinitely, producing bubble universes with diverse physical features. String theory also adds to this idea, proposing that there are many possible setups for the universe's building blocks, suggesting our universe is just one among countless configurations in a vast landscape. Now, could we ever crack the mystery of the multiverse? Despite its exciting promises, testing the multiverse theory is a tough nut to crack due to its very nature. The main hurdles to testing it include cosmic isolation. Universes in the multiverse are seen as being causally separated, meaning events in one wouldn't directly affect another. This isolation makes seeing or connecting with other universes extremely hard. Then there's the lack of strong evidence. So far, there's no direct observational or experimental proof of parallel universes. The multiverse idea remains mostly theoretical and based on intricate mathematical models, which makes it tough to verify physically. And let's not forget the cosmic scale. The sheer magnitude of potentially countless universes scattered all over makes gathering data or running experiments really daunting. Still, despite these challenges, some scientists are exploring indirect methods to test parts of the multiverse theory. The cosmic microwave background, CMB, could reveal insights into other universes, and any odd patterns or anomalies might indicate interactions with other universes during cosmic inflation. Additionally, string theory, which folds the multiverse concept into its framework, might offer predictions or limits that might be tested in high-energy particle physics experiments. If scientists find signs that match what string theory predicts, it could give a boost to the idea of a multiverse. Spotting any unusual phenomena or unique physical constants predicted by multiverse theory in other universes could be key. Basically, although proving the multiverse directly is super challenging, researchers are on the lookout with the knowledge and tools we have right now. Fingers crossed, we'll solve this mystery in our lifetime. We've already chatted about some cool space and time theories. Now it's time to jump into the final building block of the universe: matter. So, what's the deal with matter anyway? It's the stuff that forms everything we can see and touch, from tiny particles to giant stars. It even makes up us. Matter is defined by some main features. First, there's mass. That's how much stuff is in an object, measured in units like kilograms or grams. Mass affects how objects weigh and how they pull on each other through gravity. Then, we have volume. Matter takes up space, and its volume tells us how much space that is. Different kinds of matter have different volumes, like how a solid is tightly packed, while gas is more spread out. Matter breaks down into tiny particles, each having its own set of traits. This includes atoms, molecules, and subatomic particles like protons, neutrons, and electrons. How these particles are arranged and how they behave is what gives matter its physical and chemical traits. When it comes to states, matter exists as solids, liquids, gases, and sometimes plasmas. These states indicate how particles are organized and move. For instance, particles in solids are tightly packed with little movement, while in gases, they are more spread out and move freely. Chemically, matter can be categorized in several ways. Elements, compounds, and mixtures are all different kinds of matter. Elements have one type of atom, compounds have different atoms bonded together, and mixtures are a combo of substances that aren't chemically bonded. Each type of matter has its own set of physical and chemical properties, like density, melting and boiling points, conductivity, and how it reacts to things. Matter isn't fixed. It can transform through chemical reactions, phase changes, or nuclear reactions, leading to all the variety we see in the universe. Matter's role is pivotal in helping us grasp the universe's structure and how it changes over time. It forms stars, planets, galaxies, and all sorts of celestial bodies. Matter interacts via gravity, electromagnetism, and nuclear forces, affecting the universe on huge and tiny scales. Let's get into the nitty-gritty of the subatomic world and explore the different states and forms of matter, revealing the intricacies of the universe. Matter consists of subatomic particles, the building blocks of atoms. The key ones are protons, neutrons, and electrons. Protons are positively charged and reside in the nucleus of atoms, crucial for identifying elements. Neutrons have no charge and sit alongside protons in the nucleus, adding to an atom's mass but not its charge. Electrons, with a negative charge, orbit around the nucleus in areas called electron clouds or energy levels. They determine how atoms behave chemically, making them crucial in reactions. Elements, the simplest form of matter, each have a unique type of atom, which is defined by how many protons are in its nucleus. The periodic table lines up all known elements by their atomic number, which corresponds to the number of protons each has. Compounds come about when two or more different elements join together chemically in set proportions, resulting in new substances with unique properties. Take water, for example. It's a compound made of 2 hydrogen atoms and 1 oxygen atom. Mixtures, however, are made up of different substances that aren't chemically bound together. Unlike compounds, mixtures don't have set ratios, and the individual parts keep their own properties. Examples include air, which is a mix of gases, salt water, that's just salt and water mixed together, and something like trail mix. Matter shows up in various states based on how its particles are arranged and moving. In solids, the particles are packed tightly together, have fixed positions, and just jiggle in place. Solids hold their shape and volume. In liquids, particles aren't as tightly packed and can slip past one another, letting them flow. They hold a definite volume, but take on the shape of their container. Gases have particles spread out and moving freely, taking up the whole space they're in. They don't have a definite shape or volume. If you crank up the temperature really high, matter can become ionized, turning into plasma. Plasma is made of positively charged ions and free-moving electrons, with stars, lightning, and neon signs all being examples of this state. Matter's different states and forms explain the complexity and variety all around us, in galaxies, stars, planets, life, and everything we observe. Understanding how matter behaves is key to grasping the natural world and exploring the universe scientifically. In our cosmic journey, we've seen the diverse and complex material world. But amid this richness, the idea of nothing prompts us to ponder the voids, the spaces missing matter. At the subatomic level, particles seem to pop in and out of existence in quantum fluctuations, while on a cosmic scale, space isn't truly empty, but filled with dark energy and cosmic background radiation. This concept of nothing challenges how we think and inspires philosophical questions. Is nothing just the lack of something, or does it have its own kind of existence? Can we really understand nothingness, or does it stay an elusive concept beyond human understanding? Thanks for watching.